Exercise 6.3. Show that any two parallel planes will have Cartesian equations ax plus by plus cz equals d1 and ax plus by plus cz equals d2, and that the plane which is further from the origin will have a bigger d value in terms of modulus. So what I mean is like -5 is bigger than 2 in terms of modulus, because the modulus of -5 is bigger than the modulus of 2. Okay, so let's envision two planes that are parallel. Not so great. Alright, whatever, that'll have to do. Then, if the vector n is normal to one of them, then it's also going to be normal to the other one. In fact, that's pretty much the definition of parallel planes there. And hence, by our calculation before, if we let this be the point P, and then this be the arbitrary point with position vector x, y, z, then we already figured out that n dotted with x, y, z is going to equal n dotted with the vector OP, and that's going to be the d coordinate. Now similarly, if we take another arbitrary x, y, z point in our plane, well, in our other plane that's parallel to the first plane, then let's call this point Q. This time we have that n dotted with x, y, z is equal to n dotted with OQ. So the d value has changed depending on what is a point that the plane goes through. And obviously, if two planes are parallel to each other and they share a point, then they have to be the same plane. It's also kind of interesting, it's not part of this problem, but it's also kind of interesting to observe that if you take another point W in the plane, then actually n dotted with OP has to be equal to n dotted with OW. And that's simply because the vector PW is inside the plane, and therefore n has to be orthogonal to it, and the vector PW is equal to OW minus OP. And so we have n dotted with PW is equal to n dotted with OW minus OP. And we know that's equal to n dotted with OW minus n dotted with OP, and that has to equal 0 because n dot PW is 0, and so therefore n dot OP is equal to n dot OW. So it doesn't actually matter what point in the plane we choose to do this calculation here. Anyway, we've proven the first part of the question. If we call this pi 1 and this plane here pi 2, then clearly pi 1 is going to have the equation. So if we say n is equal to n1, n2, n3, then clearly pi 1 is going to have the equation n1x plus n2y plus n3z. And then let's call this constant number n dot OP. Let's just call that d1. And pi 2, by the same calculation, because this is the same vector n, is going to have the equation n1x plus n2y plus n3z. So that's expanding this out, is equal to the constant n dot OQ, which is equal to d2. Let's just call it d2. Okay, so that takes care of the first bit here, but the second bit seems to be a bit trickier, and the plane which is further from the origin O will have a bigger d value in terms of modulus. Alright, let's go ahead and draw a new picture then. Let's make some bigger planes. Alright, so this is the first plane, pi 1. And then this can be the second plane down here, pi 2. Now there's three situations to consider. Basically, the origin, well, two situations to consider really, because the planes are arbitrarily defined anyway. Either the origin is on one side of both of them, or the origin is between both of them. Let's suppose that the origin is on one side of both of them first. And let's take the normal vector that is normal to both of the planes since they're parallel, and let's extend it. So let's say this is our normal vector n, which is normal to both of these two planes. And then if we go ahead and extend it, so we're going to hit the first plane somewhere. And then we're going to hit the second plane somewhere. So let's suppose we hit the first plane at k times n, or we hit the second plane at k times n, doesn't really matter. And then let's say we hit the other plane at, I don't know, a times n. Now clearly the length of kn, which is equal to the length of k, or the k is a real number, sorry, the modulus of k times the length of the vector n. This is what we would say is the distance from the plane pi 2 to the origin. And an, the length of an, which is equal to the absolute value of a times the length of n. This is the distance of pi 1 to the origin. And clearly we also have that the absolute value of a is bigger than the absolute value of k. Now observe that an is equal to an1, an2, an3. So that is a point inside of the plane. That means a point inside the plane has coordinates an1, an2, and an3. And if we recall the equation of the plane pi 1, that's going to be n1x plus n2y plus n3z is equal to d1. So if we sub in x equals an1, y equals an2, and z equals an3, since this is a point on the plane, it should obey this equation. And so we can quickly calculate that d1, just by substituting into this equation here, d1 is equal to a times n1 squared plus b, no, not b, still a, a times n2 squared plus a times n3 squared, which is equal to a times the length of n squared. And similarly, since pi 2 has the equation n1x plus n2y plus n3z is equal to d2, we can get that d2 is equal to k times the length of n squared. Therefore, since we have the absolute value of a is bigger than the absolute value of k, that gives us that the absolute value of d1 is bigger than the absolute value of d2. So when the origin is on one side of the two planes, clearly the one that is further away has the bigger d value in absolute value. And if instead we have the origin is in the middle of the two planes, you can make the exact same argument, because nowhere here did I assume that a is positive or negative or k is positive or negative. So you can still take the vector an and you can still take the vector kn, where this time k would be less than 0 if n is going in that direction, but it doesn't really matter. The argument is the exact same. Whichever one is further from the origin, suppose that pi 1 is further from the origin, then again that would imply that the absolute value of a is bigger than the absolute value of k. And so the same argument holds. And that's all. If instead we were to suppose that the origin is on this side, it's just a repeat of the first argument, where I guess if n is going in this direction, a and k would both be negative. And they would exchange roles somewhat, because in that case we would have the absolute value of a. If this vector here is a times n, we would have the absolute value of a less than the absolute value of k. But it doesn't really matter. Okay, so that's exercise 6.3.